In this lesson, we will look at the definition and end behavior of polynomials. Let's start with the definition. A polynomial function is a function of the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus all in-between terms up to plus a sub 1x plus a sub 0, where a sub 0, a sub 1, on all in-between coefficients up to a sub n are real numbers, and n is a non-negative integer. The domain of a polynomial function is all real numbers. Are the following polynomial functions? F of x equals x squared minus 5x plus 3. Yes, this is a polynomial. G of x equals negative 2 is also a polynomial. It might help to think of this as negative 2 times x raised to the 0 power. H of x equals x minus 5 square root of x plus 3 is not a polynomial. Square root of x is equal to x raised to the 1/2 power. In polynomials, exponents must be integers. R of x equals negative 1 over x is also not a polynomial. 1 over x is equal to x raised to the negative 1 power, and for polynomials, exponents must be integers that are greater than or equal to 0. Properties of polynomials. The example, f of x equals negative 3x to the 5th plus 4x cubed minus 2x squared plus 1 has a degree of 5, the highest power of x in our polynomial. The leading term is the term that contains that degree of 5, would be negative 3 x to the 5th. The leading coefficient is the coefficient of the leading term, which is negative 3 here. The constant term is 1. What about the degree of g of x equals 0? That is actually not defined. However, if we would have g of x equals 3, that would be defined as being a degree of 0. So g of x equals 3 has a degree of 0. The end behavior. For the end behavior of a function f of x, we will look at the leading term a sub n x to the n. We will start by looking at a being greater than 0 and n even. Here the end behavior will resemble that of y equals x squared. For the end behavior, we look at what's happening with the end of the graph as the graph goes out to positive or negative infinity. Here, as x approaches negative infinity, f of x approaches positive infinity, and as x approaches positive infinity, f of x approaches positive infinity. If we have a being less than 0 and n is even, our end behavior will resemble that of y equals negative x squared. As x approaches negative infinity, f of x approaches negative infinity, and as x approaches positive infinity, f of x approaches negative infinity. When n is odd and a is greater than 0, we have end behavior resembling y equals x cubed. As x approaches negative infinity, f of x approaches negative infinity, and as x approaches positive infinity, f of x approaches positive infinity. When a is less than 0, our end behavior resembles y equals negative x cubed. As x approaches negative infinity, f of x approaches infinity, and as x approaches infinity, f of x approaches negative infinity. Let's find the end behavior of the polynomial f of x equals negative 2x cubed plus x minus 5. We look for the leading term, which is negative 2x cubed. So here a would be negative and n would be odd. Our end behavior would resemble that of y equals negative x cubed. So let's see if I can sketch y equals negative x cubed, just a quick graph here to get the end behavior. As x approaches negative infinity, f of x is approaching positive infinity, and as x approaches positive infinity, f of x approaches negative infinity. So this would be your solution here if you were asked to find the end behavior. What about g of x equals 2x to the fourth minus x squared plus 1? Here a is positive and n is even. So our n behavior would resemble that of y equals x squared, which would mean that as x approaches negative infinity, g of x approaches positive infinity, and as x approaches positive infinity, g of x approaches infinity. Try on your own. Find the n behavior of the polynomial function f of x equals negative 2x to the 8th plus 3x to the 5th minus x cubed plus 2x minus 1.